Hello everyone, in this video we are going to talk about engineering specifications. So hopefully by the end of this video you know what are the specifications, why do we need them, how can we establish them, and what are the metrics and values. But let's look at the review of what we talked in the previous lecture, which was need analysis process or customer needs. So can you tell which of the following is not part of the need analysis process? You did an exercise for this one. A, gather raw data for customers. That's something that we need to do. We can collect data by conducting a survey. We can interpret raw data. Developing concepts, that's not part of the need analysis. So the answer is part D. Organize into a hierarchy. We can organize our data into a hierarchy. Let's look at another example. Here is the result of a survey for people who have had concern dropping their cell phones, and they have mentioned that they have dropped a cell phone in a toilet. 31% have dropped it in some sort of water, dropped it on the floor, spilled coffee, and then the last one is just a random item on the survey. But what do we know after looking at this survey? What does the customer really need? What would be the need statement? Do we need the cell phone to have a strap? That talks about the solution. That's not what we are trying to find yet. The cell phone will work after it's dropped in water. The cell phone should work underwater. The cell phone has a seal between all connecting pieces. The cell phone may crack after it's dropped. So what would be the customer needs? The customer needs would be the cell phone will work after it is dropped in water. Part A talks about the solution. At this stage, we just want to talk about the need. Part C is over design. That's not what the customer wants, doesn't want it to work underwater. Part D is also talking about the solution. How we're going to achieve that it works after dropped in water is something that we do in concept generation. And the last one would be irrelevant. So we have talked about the customer needs. Now we are going to talk about the design specifications. So we develop the specification so we are on the same page with the customer. So here is a cartoon, but there's a lot of truth about it. If you look at it, this is how the customer explained the project. The project leader understood it. The engineer, as always, over-designed it and make it more complex. How the programmer wrote it, and the salespeople exaggerated what it can do. You can see there is a sofa here, and then this is more than the truth. The project was how the project was documented. A lot of time documentation is not present. And then how the customer was billed. The billing department doesn't care about the design process. And then at the end, what the customer really needed. So what the customer needed was not the same as what the customer explained it. So if you are on the same page and understand the customer needs better than the customer, we could have a real good design. But what is the design specification? We want a precise description of what the product needs to do or has to do. We want to make sure it's unambiguous, and we want to make sure it has metric and values. So this is what makes the specification different than the customer needs. The specs has a metric and has a value associated with it. So we can evaluate our design to see if it is met the specs or not. Should talk about what it can do, not the solution. We can categorize our specs based on a goal or a constraint. So each spec is going to be either goal or a constraint. And the goal is a wish list that is better to have, but it hasn't failed if it doesn't reach that. And usually for the goal, we are trying to minimize or maximize something. For a constraint is a must. Let's say that there is a constraint about the dimension that we need to have. So there's specific value for width and length and height. And if we don't meet that, our design has failed. Let's look at an example of a specification so to understand what we mean by design specs. Let's say we're going to develop a specification for a chair, and it's just two specs. A design could have 20, 30 specs. The customer needs is the chair needs to be strong, and we call it marketing specification. Another name for marketing specification is customer needs. So this is vague to us. We want something actual value associated with it. So what is the specs? The chair needs to be able to handle 400 pounds. What metric we're going to use? We're going to use force. What value? 400 pounds. Why 400? That's a lot of times the sponsor provides it. Sometimes we find that by doing research. And then is it a goal or a constraint? Is a constraint that we need to have. The chair needs to be as light as possible. So that's the goal. We're trying to minimize the weight. Also, the metric is the weight. We can measure the weight of the chair, and also the value would be 10 pounds. It should be less than 10 pounds. So it's kind of a constraint and a goal. So a goal is something that we try to achieve, but it's not necessarily essential. Let's say for an example of a razor, we want something to last as long as possible on a set of batteries, and it's to be as light as possible. So we want to maximize the life on batteries and also minimize the weight. So always remember, if you're maximizing something or minimizing, that's the goal. And you could rank your goals to see which one is more important than the other ones. But a constraint is a very given specific values that you need to follow, otherwise the design has failed. If the customer wants at least 45 minutes on a razor because that's how long it takes to shave, then that's your constraint. If it wants to be 400 grams, then that's the constraint, and that's the rigid. Sometimes the constraint could be flexible if you're talking about a razor. It's not as important, let's say, as aerospace products. So you might say that, okay, so 400 but 401 is okay. And sometimes it's very rigid. Again, example of medical field or aerospace, that there is a limit on the temperature that you need to have, a dimension that you need to follow, and you have a rigid constraint. So your design specification can be categorized into goals and constraints. It's either or, and there is scenarios that we could have both as well. But for goals, we are trying to minimize or maximize, make it as light as possible, as cheap as possible, smallest, larger, make it quicker or longer. And constraints are specific values on weight, on size, on cost, on the reliability, and so forth. So let's think about the goals and constraints that we could have for a chair. Let's say you are designing a chair. What goals can you think of? You could pause the video and write down the goals and write down the constraints that you need to have in your specification. So the goal that I can think of, it can be as light as possible. It could be as comfortable as possible. It could be as ergonomic as possible. It could be as cheap as possible. So the price, the constraint that we can have is the width. It needs to fit in a doorway. You can't make it so comfortable that it won't fit anywhere. You could put a limit on the cost that it needs to be. We talked about the cost to be a goal, but also it can be a constraint that doesn't go more than that. And remember, for specs, the difference between a spec and customer need is that the specs have a specific values and metric for it. So if you're saying that to be a specific cost is a constraint, we need to put a value. It should not cost more than, let's say, $75. Or if we have the width as a constraint, we need to find the door width in typical rooms and put that as a constraint value, 32 inch, 36 inch. And some specs is a little bit harder to put a constraints on them. Let's say we're talking about comfortability. So if we want the chair to be as comfortable as possible, but how do you put a metric for it? It's very subjective. A lot of times for those specs, we need to put a survey. We need to survey 10 people and ask them to rank it from 1 to 10, 10 being the best, and then put a pass or fail criteria, saying that if it is more than 7 on the average of 10 people, then we have met our specification. As we talked, there are some goals that that are constrained as well. Let's say we want the weight to be less than 10 kilograms, but also we want it to be as light as possible. We want the cost to be $75. That's our constraint, that's our limit. That's the upper limit, but also the cheaper, the better. So these are the examples that can be goals and constraint. And a lot of times we could have scenarios that the cost is only a constraint. As long as it's $75 less, we don't really care how much it is. So you don't need to try to make it as cheap as possible. Let's look at an example of this razor. The razor weighs less than 400 grams. This is a very good specification because it's not vague and it has a value. For specs, we need values. 400 grams. What is not a good spec is that if you say the razor weighs less, it doesn't have any value, it's vague. I don't know what you mean by weigh less. Or if you say the razor is small, or only has one battery, or is light. So here in these three scenarios, we are talking about a solution. How to achieve lower weight. We don't want to talk about the solution yet. This is a specification. We want to keep it open. So the design could be in any of them. We talk about the concepts later on. Or so here the razor should weigh less than 400 grams. Everything is good here, but the word should means, well, it's not a constraint. It doesn't have to, so we don't want to use the word should and must in our specs. Let's see which one is not an acceptable specification for a portable electric wheat trimmer. So if you have a wheat trimmer, which one is not acceptable? The trimmer turns off when released. The trimmer weighs less than 5 pounds. The trimmer costs less than 50. The blades are replaceable, and to reduce noise, the trimmer must have a quieter motor. So this one is not acceptable because it talks about the solution. The first one is a specs that it turns off when released, so it's a pass and fail. But also even for this one, we would like to put a value for it. So the trimmer turns off. How do we put a value for it? We could say that it turns off after 5 seconds when released, after 10 seconds. So when we design it, we could go back to our specs and evaluate it. Or the trimmer blades are replaceable. Again, this is pass or fail. This is a constraint that we have, but also we want to put a value for it. How do we put a value? Say the trimmer blades are replaceable within 1 minute or within 30 seconds, whatever value you want to put in, because everything is replaceable given enough time. So that's why for specs we need values. Let's do another exercise. Let's say you want to design a car and we want to find specs for these need statement for customer needs. We said the difference between customer needs and specs is that value. We want the car to be fuel efficient, so the customer wants it to be fuel efficient. What is the metric for it? We have a good metric for this. That's called MPG, mile per gallon. We can put an MPG of 30 miles per gallon. We want it to be better than that. Where do we get that 30? From a sponsor, maybe from research that the customers want this. But some are a little bit more challenging. The car handled well. This is very subjective. To me, the car might handle well. To you, it might be awful. That's why we need to develop the specs to make it quantitative as opposed to qualitative. How do we put that? We could do a survey of people driving it and see what they say. We could put a value of the corner radius. What is the corner radius this car can handle? We could talk about lateral acceleration. We could talk about the grip between the tires and the road, the coefficient of friction. So we could put these values, and sometimes we could use all of them. Do A, B, C, D, and see which one it meets. And that would be our criterion for handling well. And the car is attractive. That's another subjective one. How do we evaluate it? Probably a survey would be best for this to see if it has met our criterion or not. Another example is a screwdriver. We're going to develop a spec to have a better grip for a screwdriver. Again, better grip could be vague. We need to clarify that. A better grip could be a precision grip, and it could be a power grip. It's very subjective and qualitative. So to develop the specs, we want to put a value and metric to that. What would be a good metric for a good grip? So if you're talking about precision grip, the good metric would be the increment of torque that we could apply, how much torque or force you could apply. Maybe 0.1 Newton meter would be the increment of the torque that you could apply to tighten or loosen something. For the power grip, we don't care about the increment, but we care about the total torque that we could apply. So we could put a specs that's saying that the screwdriver should be able to handle that amount of total torque. And then once we design our screwdriver geometry, then we do prototyping and we could test it and say, oh, we met that specs or we failed it. But if we don't develop the specs, we really don't know. It's very subjective. I think it's a good grip, you think it's not. But to go through an example, we want to design a specs for a wheelchair. Let's say you are hired by a company to develop a new wheelchair design, which would be very interesting project. And what do you have is that I need to be able to get around easily. So it's a little bit vague. The customer wants easy transportation, but in terms of engineering specs, we can say, okay, the easy transportation could mean that it needs to fit through standard doorways and it needs to be lightweight. What is the metric? The metric would be easy. For the wheelchair, we need to have width, and for the weight, we're going to measure the weight. But how are we going to find the values for it? We have to do research to know what is the typical door width in the US, or what is the typical weight of the wheelchair on the market. We don't want to be the heaviest one on the market, and we want to make sure it fits into every door. When we do research and find the building standards, we find that, okay, that's 32 inch is the interior and 36 inch. And we find another standard as well for the length, because it has to go through the corner. So to have a good corner, 48. So we could add even another specs, not only for the width, but also for the length. That's what we come up with the research for our design before we start generating concepts. And if you look at the wheelchair weight on the market, we can, let's say, find 3 wheelchairs, the lightweight, the cost, and the capacity. The weight, 26 is the highest, but also it has the highest capacity. So we need to make sure that we are not heavier than the heaviest. You could even be more strict, and you want to be the lightest, so you put 19.5. It really depends on what you try to achieve. So after research, we find out 32 is the value there for our design. And also 26 pounds would be the maximum weight that we need to have. And that is a constraint for us. We do not want to be larger than 32 inch in width, because even if it's 33, it's not gonna fit. So it's the constraint. And it's not a goal. We are not trying to minimize the width, because it needs to be comfortable. Somebody needs to be able to sit there. And the weight is also a constraint. We don't want to be the heaviest than all. But also it could be a goal as well. We don't want to be heavier than 26, but it could be as light as possible. So this is the one that is both a constraint and a goal. Let's look at some other aspects for that wheelchair design. We want it to be cost effective. We want it to be aesthetically pleasing. So for the cost, the metric is easy, it's the cost. And for aesthetically pleasing, we can do a survey. So for the value, let's say we assign a 2,500. How did you get the value? From the sponsor, from the customer, from the designer. So, and also 7 out of, if you're going to average 20 people, how did you get the number of 7 for our survey? That's something that you can come up with your team, saying that this is the number that we are going to use. Now that we have the metric and the value, we can put our specs together. This is an engineering specs because it has a value. The design must cost less than 2,500. The design must have an average rating of 7 out of 10. And then because we have these values, after we complete our design, we can come back and look at our specs and say that, okay, we have met these specs. Put a check mark or put an X saying that we did not meet these specs. Our design failed. And here is the realistic constraints that we talked about. We could have another column and call it what realistic constraint it addresses. So cost would be economic. And we have other realistic constraints. These are good to think about it. once you complete your spec list to see if you're missing anything, or are we missing about manufacturability, are we thinking about safety, how can we assign specs for that. Now that we have learned about the specs, can we say why we have specs or which one is not a good reason? Let's look at the first one. Translate customer needs into measurable design targets. Probably this is the most important reason that we have specs. We want measurable targets, something that we can measure and evaluate. We want the product to be as inexpensive as possible? Definitely not. So B is the answer here. Help resolve trade-off between conflicting needs. That could be a good reason for developing specs. We want to know which one is more important, which one is the goal, which one is the constraint. Ensure the final design has met all the customer's constraints and all the customer needs. And that's another reason for developing specs, to see what the customer needs are and bring them into specific values. So as part of the homework for this week, you are going to develop specs for the topic that you chose for previous lab group. This is an individual work. So you're going to come up with 10 specs and you're going to find a metric and value. So learn how to find a metric and value and then develop your engineering specs. Engineering specs needs to have a value for it. For some of the stuff it's easy to put a value in. For some of the stuff it's a little bit harder. You need to think a little bit. And you could break it down into part A or B. Again, this is individual. Make sure you complete it by the deadline.